What is up, people? Welcome to the session. Welcome to Vedantu 9th and 10th English channel. I hope all of you guys are doing really well. I know it's a Sunday, so first of all, thanks a lot for spending your time with me. Today's session is going to be for ICSE students, or for all the ICSE students out there. This is the Prodigy series for Refraction of Light at Plane Surfaces session number 2. So we have already done the first part of this. So if you haven't checked that out yet, make sure you check that out as well, because that is going to help you to understand this chapter a little bit better. If you guys are struggling with this particular chapter and you want one video where you can understand everything in just 1 hour duration, then please do check that out as well. My name is Anoop and I'm a master teacher of physics here at Vedantu. A very warm welcome to all of you guys out there. And first of all, happy Sunday. I know it's a Sunday, so thank you once again for joining with me, guys. All right, so people, welcome once again to today's session. In today's session, like I told you guys, we are going to be doing the one-shot series of refraction of light at plane surfaces. Now, if you remember, we have done pretty much a lot of the topics in the previous session. We understood about refraction, we understood about laws of refraction, refractive index, factors affecting refraction, and principle of reversibility. So these are some of the topics that we have done in the previous session. Today, we'll understand a little bit about real and apparent depth. What exactly is critical angle? How does total internal reflection happen? And if total internal is something that happens, how does it happen in a prism as well? And I'll also tell you some extra information about where total internal reflection are used and such. What are the applications of that? I'll be talking about that also a little. All right, so without wasting any time, let's get into the topic: real and apparent depth. What exactly is this? What do you mean by real depth and apparent depth? Now, guys, I don't know if you remember this. Probably, you'd have probably watched some of the videos of this. There's this little experiment. What they do is that they put a coin inside a cup, right? And what you notice is that the person starts to walk behind. If you have time, please do check that out. Check that out. It's it's a simple coin. They put it in a bowl and they just start walking backwards. All right. Now, after some time, the bowl, because it's opaque, it does not allow the light to pass through it. So in other words, you will not be able to see the coin after you move certain distance, right? You'll not be able to see the coin anymore. But if you were to put some water into that bowl, magically, all of a sudden, the coin appears. What is the reason for it? Now, let me tell you this. It's not that the coin is floating, because coin is it's more denser than water. So it's not that when you pour water into it, the coin starts floating. That doesn't happen. So what is the reason that you're able to see the coin all of a sudden when you pour water into it? Here's what happens, guys. When you pour water into it, light undergoes a process known as refraction. Now, you already know what refraction is. The bending of ray of light is what is known as refraction. So what happens is that because light is entering from water to air, it undergoes refraction and it falls into your eyes. I keep telling this statement: our eyes are absolute fools. It's just as plain. It's as plain as it gets, because our eyes can be easily tricked. All these magic tricks. Why are they called as tricks? Because it's an illusion. Your eyes are not able to keep up with that. So you think that it's something supernatural, but it's not. It's just a simple trick. So here also what's happening is that when the light falls into your eyes after refraction, when your eyes are trying to trace back the source of light, it appears as though the coin is present a little bit more higher than its actual position. So that is what is called as the apparent depth. So what you see is not the actual coin. What you see is an illusion, the image of the coin. That is what is called the apparent depth. And where the coin actually is in the water or in that container, that would be called as the real depth. Simple. So real depth is the actual position of the coin, or the actual position of the object. Apparent depth is nothing but the thing that you see, the thing that appears in front of you, thing that is not, it's not the actual object, but it looks like as though it is there. So it is nothing but the depth of the object in the denser medium when seen from the rarer medium. That is what is called as the apparent depth. And one peculiar thing about this apparent depth is, guys, that the apparent depth value would always be lesser than the real depth. So if you look at over here also, the fish is actually much more lower than the person what he's seeing. So the apparent depth is a little bit more higher than the real depth. Now, in fact, guys, in your ICSE syllabus, you have an entire proof for this. There's an entire proof why it is, what is the reason that apparent depth is, much lesser than real depth. So what we're going to do right now is quickly, I'll just show you the proof as well. Now, it's important that you go through this proof, and it's more important that you practice it on your own accord. Make sure that you practice it. Take your Selina book. Make sure that you guys practice this what do you call this derivation over and over again until you are able to do it without having to by heart it, or without having to cramp up the entire thing. All right, so here's the thing. Let's say there's a coin. All right, and this coin is at this position O. The coin is present at this position O. Let me just show that with a different color so that you guys can make it out. So you see this? This is the coin O. All right. Now, light is originating or light is coming out from this coin. You can say that this is the ray of light, this is another ray of light, and since this ray of light is incidenting normally to the surface, it will pass through undeviated, or there will be no refraction, and this ray of light would pass through straight. But the other ray of light, because it's incidenting obliquely, there will be some refraction, and after refraction the light will reach into your eyes. So this is the angle of incidence here. This is the angle of incidence for the denser medium right here. This is the angle of incidence, and this is the angle of refraction. That is, the ray of light is undergoing some refraction and then reaching your eyes. Now, if you look very carefully, guys, you can notice that this OA dash, and n dash n, which is nothing but the normal, is actually parallel to each other. If you look very carefully, they're parallel to each other. Since they're parallel to each other, we can say that this line that you see, let me just show that with a different color. I'm going to use, I believe, black color. I think that's better. So this ray and this one, these two lines that you see, basically IB and OB, both will behave like transverse. Now, if you remember, guys, if there are two lines which are parallel, the line that is, which is intersecting both these parallel lines, that is called as a transverse. So here you have two transverse. All right. So look, let me just consider the first one. All right. I'm going to talk about this one now. OB. All right. If I look at this line OB, this ray of light OB, if you look very carefully, it basically forms a right angle triangle, doesn't it? It basically forms a right angle triangle, which is nothing but AOB. Now, if I just forget about the right angle triangle for a second. If I just forget about that, ignore it for 1 second. If you just look at this angles alone, you can see that this angle I and this angle O, that is AOB and ABN, they are both alternate interior angles, right? These are both alternate interior angles. So you can say that if this is I, you can say that this is also I. Simple. Now, if I take the other transverse, that is IB, line IB, this is R. According to corresponding angle theory, I'm sure that you guys all remember corresponding angle. According to corresponding angle theory, we know that these both would be also equal. So if this is R, then this will also be R. Simple. Now, guys, I'm going to go to the triangle. Now I'm going to assume that I'm going to take this as one triangle, which is nothing but triangle AOB as one triangle, and triangle AIB as another triangle. AIB is another triangle and AOB is another triangle. All right. So I hope you guys understood the basic part. All right. So this is how you got, I hope you understood the nomenclature. This is how you got the nomenclature. All right. So what is this position I? Let me tell you that also. This position I is nothing but the apparent position. That is nothing but the apparent position. And O is nothing but the real position of that particular object. O is the original or the real depth, and I is nothing but the apparent depth that your eyes are actually seeing. Okay, now guys, let's go to the actual derivation. Since I've already covered this up, we know that angle AOB is equal to angle OBN dash, which is equal to I. And we also know that BIA dash and CBN, which is nothing but this one, that is this BIA, this angle, and this one, that is BN, and you can call it as C. All of those, they have corresponding angles. So because they're corresponding angles, you can say that they are also equal. They are also equal to each other. All right. So that's how you got this theory right now. All right. That's how you got this one. Now, here's the thing, guys. If I consider the first triangle, if I consider the first right angle triangle, that is nothing but triangle AOB. If I just talk about this triangle, this is angle I. Now, according to trigonometry, we know that sine of I, that is sine theta, is nothing but opposite divided by hypotenuse. Now, what is the opposite angle here? It is nothing but AB. So opposite is nothing but AB divided by what is the hypotenuse? Hypotenuse is nothing but, you can say that it's BO. BO is nothing but the hypotenuse. So you can say that sin I is equal to AB by BO or OB. How are you going to put it? Now what I'm going to do is I'm going to take the other triangle. All right, I'm going to take the next triangle. Okay, I'm just going to erase this one. All right. Okay, I just erased everything. That's amazing. Thank you. Super awesome. You are a genius. All right. Now, let's take this other triangle. All right. I'm going to take another triangle, which is nothing but ABI. So if I take triangle ABI, if I take triangle AB and I know that sine R is equal to what? Opposite by hypotenuse. How opposite is nothing but AB and hypotenuse is nothing but IB. Simple. So AB by IB is nothing but the hypotenuse. Simple. So that is nothing but sin I by sin R. That's what you got here. Now, according to Snell's law, we know that refractive index of one medium with respect to other is nothing but sin I by sin R. In this case, I can say that refractive index of air with respect to the medium. I don't know what the medium is. It can be either water or glass, whatever it is nothing but sin I divided by sin R. Simple. Snell's law, your second law of refraction, you know that it's sin I by sin R. Now what I'm going to do is I'm going to substitute the values for sin I and sin R. Alright, I'm going to just substitute the values for sin I and sin R. So here's what I got is refractive index of air with respect to the medium is sin I by sin R. Sin I, we know that is nothing but BA by OB, which we already saw, which I unfortunately erased. So if I just go back to that one more time, guys, if I'll just erase this one out, and if I just take this particular triangle right here, if I take this particular triangle right here, if I take triangle AOB, we know that sin I is nothing but AB divided by sin I. Let me just write that also. Sin I is nothing but AB by sin I is equal to AB whole divided by OB. That is opposite by hypotenuse. So I'm just going to substitute that value over here. So I get it as AB divided by OB whole divided by sin R is what? AB by IB. AB divided by IB. Now AB will get cancelled. IB will go to the numerator. So you can say that refractive index of A, that is air with respect to the medium, is IB divided by OB. IB, that is nothing but this distance, divided by OB. Simple. That's it. That's how I'm getting that the refractive index of air with respect to the medium is IB divided by OB. Now, if I want to find out the refractive index of the medium with respect to air, what will I do? I'll find out the reciprocal of that, because see, refractive index of air with respect to the medium is IB divided by OB. That's what we just got. It's nothing but IB divided by OB. So if I want to find out the refractive index of the medium with respect to air, so refractive index of the medium with respect to air will be reciprocal of that. It will be 1 by refractive index of air with respect to the medium, which is nothing but what? OB divided by IB. In other words, it's nothing but the reciprocal of that. Simple. Now guys, here's the thing. Let's say that this person right here, imagine that's you are seeing from this point now. All right, this ray of light is coming from here and you're seeing from there. Now, when you're seeing from there, can you just notice this? If you just notice very carefully, you can see that this distance AB is actually not that far. It's actually not that great. It's not like it's 1 kilometer, 2 kilometers. It's a couple of centimeters, maybe a couple of millimeters away. So what I can do is I can say that this distance AB, or this distance, you can say that what is that? This distance OB, what is that? OB can be said that it is almost equal to IA or OA, because that distance is almost equal, right? That distance is almost equal. So I can say that because it's almost the same, or it's very, very small, I can say that that distance OB that you have is nothing but OA. And here again, this distance IB can be said that it's nothing but IA. Right, because it's very, very close to each other. So what I'm going to do is I'm going to substitute that over here right now. All right, I'm going to substitute that in my equation, and this is what I'm going to get. That is, in place, this is the equation that I'm going to take. All right, refractive index of the medium with respect to air is OB divided by IB. Since that distance, since A and B are very, very close to each other, it's only a couple of millimeters, couple of centimeters away. So I can say that A is almost equal to B. So I can say that instead of OB, I will write it as OA. And instead of IB, I will write it as IA. Because the distance is almost equal. It's very, very close to each other. So this is how, people, you are proving that refractive index of a medium with respect to air is equal to the real depth divided by the apparent depth. Let me tell you why. Because if you go back to this equation, if you go back to this diagram, you know that OA is nothing but the real depth of the object. That is where the coin is actually placed. And AI is nothing but the apparent depth. That is where you're seeing the image. So in other words, you're just basically proving that real depth by apparent depth will give you the refractive index of that medium. That's all. So again, guys, don't by heart it. Don't have to by heart it. If you can just draw the the diagram that you just saw right now, if you can just draw the diagram, you can derive it all by yourself. You don't have to by heart or cramp up the entire thing. There's no need for that at all. All right. That is why I explain it step by step. I could have just told this is the thing, this is the thing. The reason why it took so long to explain it is because I want you guys to understand that this particular derivation is not that difficult. It's just a little bit of practice, a little bit of understanding of the concept will help you to easily do it. So please remember it. Once again, people, go back to it. If you have to, please go back 5 minutes before when I started this particular derivation. Go through it one more time if you have to, but make sure you understand it. Do not by heart it. All right. Okay. Now, here's the thing, guys. We also know that shift, that is nothing but the difference between the real and apparent depth, is nothing but real depth minus apparent depth. That will tell you the shift, that is by how much the object has moved from the actual position and from what you see. Now, from the formula, we know that refractive index of the medium with respect to air is nothing but real depth divided by apparent depth. So I can say that apparent depth, if I take this to the other side, I can say that apparent depth is equal to real depth divided by the refractive index of the medium with respect to air. So that's what I got. Now what I'm going to do is I'm going to substitute this value in place of apparent depth. So what I'm going to do is shift is equal to real depth minus real depth divided by the refractive index of the medium with respect to air. I'm just substituting the value there because we already know that refractive index of medium is nothing but real depth divided by apparent depth. I'm just substituting that here. That's all, nothing else. Now I can take the real depth outside because it's common. So I can say that RD, that is real depth, is equal to 1 by refractive index of the medium with respect to air. It is nothing but 1 by refractive index of the medium with respect to air. So sorry, minus 1. All right, sorry about that, people. Instead of writing, I was so distracted about the camera thing. I thought, I was on full screen. All right, so I can say that refractive, when I take the real depth outside, I can write it as 1 minus 1 by refractive index of the medium with respect to air. So this is another formula to find out the shift. So sometimes people, what they lose it, they might ask you to find out the shift. They might give you the real depth of the medium and they might give you the refractive index, and you might be asked to find out the shift. So if you use this particular formula, shift is equal to real depth into 1 minus 1 by refractive index of the medium, you'll be able to get the shift of that particular shift in that particular medium. All right, so that is one more small little derivation that you must remember. Now to talk about factors, guys, because there are a few things that it depends on. There are a few factors that shift depends on. It's not that always it'll be, for example, if I keep a coin in glass and in water, the shift might not be the same. It will definitely not be the same. So first thing is, it depends on the refractive index. For example, water has a refractive index of 1.33. And if you talk about glass, it has a refractive index of 1.5. So this value of refractive index is definitely one of the key factors that affects shift in that particular medium. Second is the thickness of the denser medium. The more the thicker the medium, the more is going to be the shift. The higher the refractive index, more the shift. More the thickness of the medium, more would be the greater would be the shift as well. Thirdly is the wavelength of light. More the wavelength, lesser would be the shift. Higher the wavelength, that means red light, in other words, because it has the highest wavelength, will have the least shift. Whereas violet, on the other hand, which has the lowest wavelength, would have the highest shift. So it's indirectly proportional to the wavelength of light as well. All right. And by that, people, we have successfully completed what is shift, what is apparent depth, and real depth. Now, the next topic we're going to understand is called as TIR, or total internal reflection. Now, to understand total internal reflection, you must first understand about something called as critical angle. Now here's the thing, guys. I think I have a small little animation I want to show you people. I hope you guys can see my. If you want, you can just copy this link as well, guys. It's an absolutely free software. You can try this out if you want to. All right, just to make it more fun, because there's no point in just reading the textbook all the time. All right, so I'm gonna what to say? I'm gonna move my screen here. You can just see this. Now look at this, guys. Light at this point of time is entering from water to air. In other words, it's entering from a denser medium into a rarer medium, from a dense medium to a rare medium. Now here's what happens. When light is if you look at this, as I increase the angle of incidence, let's say the angle of incidence is around 25 degrees, angle of refraction is somewhere around 32 degrees. If I, let's say, increase it to 30 degrees, then angle of refraction becomes almost around 40 degrees. So you can see that as I increase my angle of incidence, angle of refraction is also it's continuously increasing. Now, at one point in time, don't you think that the angle of refraction will almost become 90 degrees as I keep on increasing my angle of incidence? At one point in time, the angle of refraction will become almost 90 degrees. That angle for which my angle of refraction becomes 90 degrees, that is what is called as critical angle. That is what is called as a critical angle. So what is critical angle? Critical angle is nothing but that angle of incidence for which my angle of refraction is 90 degrees. You can see this, It's, in other words, it's passing on the surface of separation. That is what is called as a critical angle. Alright, critical angle. Now, here's the thing, guys. If I were to go beyond the critical angle, let's say I decide to go beyond the critical angle. If I go beyond the critical angle, what will happen is that there's no more refraction after that. There is no more refraction. In fact, 100% of the light, if you check the intensity, 100% of the light is getting reflected back into the same medium. This is what is called as TIR, or total internal reflection. That is, light is no more getting refracted. All of the light, 100% of the light is getting reflected back into the same medium. That is what is called as TIR, or total internal reflection. But yeah, there are two conditions. One is that light has to be traveling from a dense medium to rare medium. It should not be from rare to dense, because what happens is that when light is, for example, let's say that light is entering from air to water. Now we know that when light is entering from a rare to dense medium, it always tends to bend towards the normal. So if I keep increasing my angle of incidence, my angle of refraction will keep on decreasing, right? So it is going towards the normal. So that is the thing. So you cannot see total internal reflection when light is entering from a rare to dense medium. It has to be going from a dense to rare medium, and the angle of incidence has to be greater than the critical angle. Only if it's greater than critical angle, then you'll be able to see total internal reflection. For example, guys, if we talk about water, the critical angle of water is around 48.8 degrees. All right, it's around 48.8 degrees. So if I go beyond, if my angle of incidence is greater than 48.8 degrees, let's say angle of incidence is around 50 degrees, then I'll be able to see total internal reflection. Otherwise, I cannot. Getting it? If it is less than that, even if it's around 48.8 also, then also I'll not be able to see total internal reflection. Then it'll be that'll be the critical angle. It has to be greater than 48.8. So it has to be 48.9 or 50 degrees. In that case, you'd be able to see total internal reflection. Alright, so that is TIR, or total internal reflection. Now there's a small derivation for this one also, a small relationship between critical angle and refractive index. It's actually quite simple, because we know that critical angle is nothing but that angle of incidence for which angle of refraction is 90 degrees. Now critical angle is generally represented by the letter C. Alright, is represented by the letter C. So we know that refractive index of air with respect to the medium, whichever it is, glass, whatever it is, that is nothing but sine C, or sine I divided by sine R. It's sine I by sine R. Now here sine I is nothing but sine C, because it is critical angle. So refractive index of the medium of air with respect to the medium is sine C divided by sine R. What is sine R here? R will be equal to 90 degrees, because during that, when the angle of incidence is basically equal to a critical angle, then the refracted ray would be forming an angle of 90 degrees, right? So it'll be sine 90. Sine 90 is nothing but 1. So we can say that refractive index of air with respect to the medium is equal to sine C. On the other hand, if I want to find out the refractive index of the medium with respect to air, then we 1 by sin c, reciprocal of that. So please do remember this one also, guys. Refractive index of the medium with respect to air or with respect to another medium would be equal to, or with respect to air in this case, is nothing but 1 by sin c. That is sine of critical angle. And we talk about what are the factors that affects this. The first one is the wavelength of light. The more the wavelength, lesser would be the critical angle, and more the temperature, lesser would be the critical angle as well, because as the temperature increases, the refractive index would decrease, and if refractive index decreases, critical angle will also keep on increasing. All right, so just to remind you guys, as the wavelength increases, critical angle will also increase. Critical angle will keep on increasing as the wavelength of light increases, and as temperature increases, temperature and refractive index are inversely proportional. So as the temperature increases, refractive index would decrease. If refractive index decreases, then your critical angle will increase. Critical angle will keep on increasing, because it's basically critical. We know that refractive index is 1 by sin c, right? So more the refractive index, lesser would be the critical angle. Lesser the refractive index, more would be the critical angle. So these are the two factors that it depends on. Wavelength of light is more, that is red light would have greater critical angle compared to violet light, and temperature also, as the temperature increases, critical angle will keep on decreasing. All right, so those are the two deciding factors. All right, guys, moving on to total, we've already seen about total internal reflection, like I told you before. So there are two conditions, people. In order for you to see total internal reflection, light has to be traveling from denser medium to rarer medium, and secondly, angle of incidence has to be greater than critical angle. If it's not, then it will undergo refraction. If it is equal to critical angle, then you'll be able to see that light refracts exactly at 90 degrees. All right, so yeah, guys, talking about the last topic for today, that is TIR through a prism. Now there are a lot of applications for TIR, guys. Let me tell you some of those fascinating things about TIR, because guys, all these, nowadays you are very much aware of fiber net connections, right? ACT fiber net, Airtel fiber net, those fiber nets, those fiber net, inside those optical fibers also, we are using the principle of total internal reflection to transmit the data as well, to transmit those packets of energy, right? We are actually using total internal reflection itself. In prisms, in periscopes, we use total internal reflection. We use total internal reflections in microscopes, in telescopes. The reason why we do it is because, if you remember, in TIR, 100% of the light is getting reflected back. See, guys, generally what happens is that when reflection happens, right, there is some amount of light is getting refracted, some amount of light getting reflected. So there's, like, if you just check over here, 68% of the light is getting refracted, and about 31% is getting reflected back. But in total internal reflection, 100% of the light gets reflected back, 100%. So there is no loss whatsoever. So because of that, we use it in a lot of places. Now you can also see TIR or total internal reflection in prisms. Like, you have three different types of prisms. You have the right angled isosceles prism, where you have 45 degrees, 90 degrees and 45 degrees. Then you have equilateral prism, all three angles are 60 degrees, and the right angled prism, where you have 30, 90 and 60 degrees as well. So all these three have different applications. For example, if we talk about the right angle isosceles prism, you can see that if you want to deviate the light by 90 degrees. See, this is the object, all right? So the ray of light is incidenting. It's incidenting normal to the surface, so it is going to pass through without any deviation. Once it goes and hits the other surface, now look at this. Light is now entering from a dense, this is the dense medium, and this is the rare medium. So light is entering from a dense to rare medium. So what will happen? It will bend away from the normal. So here, if you look at this, the angle of incidence is around 45 degrees. Now the critical angle for glass is somewhere around 42 degrees. So it's greater than the critical angle. So because 45 degrees is greater than critical angle, you can see that what will happen is that it will undergo total internal reflection. So it'll get reflected back. So both these rays of light will get reflected back, and the image will be oriented or deviated by 90 degrees. This is the object. You see that this is the image of that object. So you're orienting or deviating the image by 90 degrees. So this is one of the applications of it. This is what is used in your periscopes as well, guys. In periscopes, what we do is that, because the problem is that if you use mirrors, the problem is that if, let's say, 100% of light is falling on it, out of 100%, maybe around 98% is getting reflected back. 2% is getting lost. And once that 98% comes and fall over here, again 2% is lost. So roughly about 95% or 94% is what is reaching your eyes. Now the problem is, guys, periscopes are used in submarines and stuff. It is used in submarines and stuff. Now in submarines, obviously every single percentage matter, because there are a lot of people's life at stake there, and because they are in the middle of the ocean, they can't really figure out even that 1% matters a lot. So because of that reason, no, you cannot take that chance. You'll not be using mirrors there. So instead of using mirrors, we use prisms instead. So when you use these kind of the right angle isosceles prism, right, it undergoes deviation and you'll be able to see a clear image without any loss whatsoever. The second one is, if you want to deviate the image or deviate the light by 180 degrees, also we use the isosceles prism again, the right angle isosceles prism. So here you see this is the object right here. So what happens is, again, the angle of incidence is greater than, it's around 45 degrees, greater than the critical angle. Here also angle of incidence is greater than 42 degrees, that is, again, it's 45 degrees, right? So it will undergo multiple total internal reflection, and it will form an image somewhere over here. So you are deviating the ray of light by 180 degrees, right? You're inverting the object. In other words, this is the object is kept inverted, and you're inverting it back, trying to make it erect, in other words, right? And apart from that, it is also used in erecting the image without any deviations also. You see this? So this is the object right here. It's placed upside down. So again, it's not incidenting normally, so it's incidenting obliquely, so it will undergo refraction, undergoes multiple total internal reflection, because it's greater than the critical angle, goes incidence on the other surface, and then comes out. So here you can see that without any deviation whatsoever, the image is getting inverted. So that is another application of the same. So basically, guys, you have three applications for one particular prism. For this one particular prism, there are three different applications: to deviate the light by 90 degrees, to deviate the light by 180 degrees, and to deviate the light without any to invert the object without any deviation. For that also we use this particular prism. Now if you go to the other equilateral prism, this is just used to deviate the light by 60 degrees. So if you want to deviate the light by 60 degrees, you can see this, it incidence normally, undergoes with passes through without any deviation, goes and hits the other surface, angle of incidence is around 60 degrees, gets reflected back at 60 degrees, greater than the critical angle again. So you see that it deviates the image in total by about 60 degrees in this particular prism. So these are all the applications of these prisms, and this, my friends, is the one-shot series of refraction of light through plane surfaces. I hope you have understood everything, and I wish you guys all the very best, guys. If you want more help, you want to gain 100% knowledge of all of these topics, this is an opportunity for you guys to crack your exams, to score that 90% above, to get into the toppers list, to get into that elite category. If you want that extra push, Vedantu is here. Vedantu's courses, Vedantu's teachers are ensuring that you are able to understand every single concept without any compromise on the quality, and you are getting an opportunity to study in in a place where you can sit in your own comfort of your home and study the whole concept without any compromise whatsoever. Unlimited live sessions, tons and tons of quizzes which will give you a good practice for your term one examinations that are coming up. Lots and lots of amazing content, lots of micro courses which would help you to strengthen strengthen those little concepts, some tiny little concepts which are much more difficult that you feel. You can strengthen those concepts as well. Premium content, all of it can be downloaded, in class doubt solving with your amazing class teachers and your Vedantu's doubt app, always at your service 24/7 to clear any doubt that arises while you're studying, and that too for any subject that you can think of: physics, chemistry, math, bio. All of the subjects would be covered over here. unlimited courses is what we are offering for you guys. Now what you have to do is, guys, it's very simple. Just click on the link. So if this is one of the videos that came out recently, you guys are watching it, so just go to the description, guys, go to the description and go to ICSE 2021-2022, because that is when your exams are going to happen. This amazing link is going to take you through the entire page of Vedantu and help you to understand the concept a lot better. So you'll have the complete school tuitions, you'll have complete exam preparations, revision courses and other micro courses as well. And here is the thing, guys, for the entire year, that is till term 2 examinations, at a very, very nominal cost of just 18,000 rupees. I know that it's a lot of money for middle class families. You know, obviously, if I had asked my parents also that I want to enter into a course for 18,000 rupees, my parents also would have got scared. They would also not accepted. But you also have EMI options, guys. You don't have to take so much tension. Just 1,500 per month. That 1,500, though, we go to Pizza Hut, or if you go to Domino's, you'll just finish it off, right? So that's how much how much valuable your how much affordable the course truly is. And if you want, you can try the 1 month program. Once you click on the 1 month program, automatically a discount code is added. So 2,340 rupees is the 1 month coupon code as well. Vedantu Classic, the difference is that you also get the doubts app, the Vedantu doubt app that I just told you, 24/7 support. That would be available for you guys for Vedantu Classic, and the price will be a little different. It will be around 23,000, so about 5,400 rupees more, but you're getting a lot more extra features there with support always available for you guys. And you can check out all of the details. And yes, guys, if you want to know how the classes would look like, so you'll be getting, this is the schedule, the entire year's schedule will be available. So what you can do is, if you want to check out the courses, so you can just check this. For example, this is one of the sessions that happened day before yesterday, that is 8th. I'm recording this video on 9th. So yeah, for you guys, it'll be day before yesterday, right? So yes, guys, you can check that. This is how the courses are going to be. This is how the classes are going to be taken. So you'll have all the amazing teachers, will be like yeah, we'll have a lot of fun, but at the same time, we'll make sure that you've understood every single concept. So you can check it out for yourself. If you just check here, 104 doubts were asked in this session, and all of that 104 doubts were clarified inside the class with the master teacher and the class teacher. And that is a massive feat, right? That gives us a lot of satisfaction to see all of the doubts being cleared inside the class itself. You'll have lots and lots of quizzes like this. You can see, the class will be filled with lots of quizzes, so you can answer those quizzes and get on the leaderboard and stuff. So you can check that out for yourself. So this is how the classes are going to be. The content are amazingly well designed. And yes, I'll also unmute students every once in a while to get your doubts cleared. On YouTube, you don't have that opportunity to unmute yourself to ask that doubt. So on Vedantu's Wave platform, you can also get unmuted, uncammed. I will be able to even see you as well. So that is me thinking, by the way. But yes, it's not me sleeping. So I can ask and get the doubts cleared. You can see this. I talked to the student for almost 5 minutes to get all of his doubt cleared for his examination. So yeah, that is how the sessions are going to be. That's how interactive the platform is. So you have an opportunity over here to change your life for better, to better prepare for your examinations as well. Right, guys? So I hope to see you in the regular sessions. So these are the dates that the new sessions are going to be starting from. So if you talk about ICSE, 4th of October, a new set of batches already started. That's only like 4-5 days ago. You've not missed out on anything. You can join those batches and go through the recordings of the previous sessions that has happened, and change that life, make it better. That's all right. So thank you for joining, guys. Thanks a lot for spending your time with me. So let's just quickly do some quiz questions also. Oh, by the way, I completely forgot about the quiz. So let's do some quiz questions. I have some quiz questions in store. Let's do the quiz questions and then we'll call it a day. All right, few quiz questions. That's all. Here's the first one. When angle of incidence is equal to the critical angle, what will be the angle of refraction? Would it be 0 degrees, 90 degrees, 45 degrees, or 30 degrees? I'll give you 10 seconds. Done. Super easy question. It's like one of the most straightforward, direct questions that can be ever asked. Anyways, I'll start the quiz in 5, 4, 3, 2, 1. The right answer to this question, guys, would be 90 degrees. Obviously, the critical angle is nothing but that angle of incidence for which angle of refraction is 90 degrees. Next question. I want you guys to put it on in the chat box. All right, here's the second one. A beam of parallel rays after falling obliquely on a plane refracting surface diverges, converges, remains parallel but gets deviated, remains parallel without any deviation. A beam of parallel rays after falling obliquely on a plane refracting surface. Super easy question, guys. I'll give you guys 5 seconds. Very, very easy. I'm hoping that you've already told me the answer. I know you have. So high five to all the people who've gotten it right. But anyways, the answer, guys, is going to be option number C. It will get deviated, but it'll still remain parallel. The emergent ray will be parallel to the incident ray. That we have seen in the previous session. Next one. If angle of incidence is greater than the critical angle, then dash would take place. Super easy question. Even I don't even have to read out the options. I'm pretty sure you've already put down the answers. Refraction, dispersion, total internal reflection, or interference. TIR, people. Total internal reflection. If it's greater than the critical angle, then it'll undergo total internal reflection. Next one. Dash is actual distance of an object beneath the surface. Real depth, apparent depth, minimum depth, or can't really say. In other words, Bhagwan Jani, sir. Bhagwan Jani. Jai Mataji. Alright, what is the answer, guys? I'll start the question 3 to 1. Sorry, the answer to this question, guys, is real depth. If the actual depth of the object is called as the real depth, and what you see is the apparent depth. And one last quiz question, people, and this is a numerical. I want you guys to try out this numerical. Before you read the options, read the question carefully. How does the refractive index of a transparent medium depend on the wavelength of light being used? Secondly, velocity of light in glass is 2 into 10 to the power of 8 meter per second, and that in air is 3 into 10 to the power of 8 meter per second. If the ray of light passes from air to glass, calculate the critical angle. Super easy question. Let's try to do that. For the first one, guys, how does the refractive index of a medium depend on the wavelength? More is the wavelength. More the wavelength. Less would be the refractive index. Please remember this, guys. In other words, wavelength and refractive index are indirectly proportional to each other. More is the wavelength, less would be the refractive index. Lesser is the wavelength, more would be the refractive index for that particular wavelength. That is the first one. Now to answer the second part of the question, you are asked to find out the critical angle. Now, first of all, guys, we know that critical angle is nothing but what? It is nothing but that angle of incidence for which angle of refraction is 90 degrees. If you remember, all I have to do is first of all find, if you remember the formula, I told you that refractive index of the medium with respect to air is 1 by sine C. Right? It is nothing but 1 by sine C. So what you can do is first find out the refractive index. How will you find out the refractive index? Refractive index of glass with respect to air is nothing but speed of light in in glass divided by speed of light in glass. Sorry, speed of light in air divided by speed of light in glass. Speed of light in air is what? 3 into 10 to the power of 8 meter per second. And in glass is 2 into 10 to the power of 8 meter per second. Gets cancelled. 3 by 2 is nothing but 1.5. 3 by 2 is nothing but 1.5. So 1.5 is the refractive index. Now put that in the equation. 1.5 is equal to 1 by sine C. So you can say that C is equal, or you can say that sine inverse of 1 by 1.5 is equal to C. So if you find this out, you'll get that sine inverse of 1 by 1.5 is nothing but, I think it's 2 by 3. So 2 by 3 should be the answer. Yes. So sine inverse of 2 by 3 would be the answer. If you want, you can find out the angle as well. You'll get it as something around 41 point some degrees, 41.2 or 41.3, something like sine inverse of 1 by 1.5. No, you'll get us 41 point some degree. That will be the critical angle. So that is the answer for that question, guys. That's it for today. Thanks a lot for joining. The link is given in the description for you to change your life completely, to change your approach towards exam, to make sure you are in the right track, because you could be studying really hard and still not be doing so well in your examination. This is an opportunity for you guys to correct those little mistakes, those silly mistakes that you guys are doing, to ensure that 100% of that, 100% completion of the syllabus is done, because it's easy to score 80, 85%. Beyond that, it requires a lot more effort, and that is an opportunity. This is an opportunity for you guys to correct that and to go through that, go beyond that limit that is there and reach that 100%. All right. So that's it for joining, guys. Thanks a lot for joining for today's session. Do not forget to like, share, subscribe. My throat is completely gone, by the way. Shouting for 1 hour. Thank you for joining. I hope you guys enjoyed it. If you did enjoy the session, if you guys did, appreciate the effort that I put in, do not forget to hit the like button as well. Thanks a lot for joining. If you feel like someone else can, be better with this video, please share that video also with them. All right. I'll see you guys soon. Take care of yourselves. Stay safe. Adios. Alvida. Ciao. Take care. Bella ciao. Bye bye, guys. See you all. Take care. Bye bye.